Imagine this. You find yourself stranded in the unfamiliar wilderness. A potential lack of primitive skills might cause some panic.
But what if chemistry could save you? Even if you don't know how to build a fire, we can use its molecular makeup to figure it out.
Let's start with, what is fire? Fire is typically a fuel and oxygen reaction resulting in energy and some form of oxide. This is classified as a combustion reaction, where a fuel reacts with oxygen gas and releases energy in the form of light and heat. Fuel can be a hydrocarbon, like methane, cellulose, or ethanol, or even a metal, like magnesium or iron. To understand why these fuels work, let's first look at the combustion reaction for the hydrocarbon methane. All forms of combustion are oxidation-reduction reactions, meaning the chemical species involved transfer electrons and result in new formed bonds. Oxidation numbers tell us the hypothetical charge of an atom if all of its bonds were fully ionic. They show the exchange of electrons as a reaction progresses, and electronegativity heavily influences this. Oxygen is the most electronegative in this equation, and we can see that it takes electrons in its new covalent bonds. Thus, it is reduced and serves as the oxidizing agent. Carbon gives electrons, in other words, is oxidized, and serves as the reducing agent. So what does this reaction actually look like? Methane and oxygen have higher potential energy than the products because they have weaker bonds. First, the reaction must be kick-started. Energy must be added to break the existing bonds, like kinetic energy from friction. Adding the total bond dissociation energy of the reactants is what overcomes the activation energy barrier. The energy added results in rapid collisions. Atoms rip apart from their original bonds and form more thermodynamically favorable ones. These optimal and strong pairings release energy. Zooming in, we see that oxygen pulls electrons compactly and thus has lower energy levels than carbon. So the potential energy lost as hydrogen atoms move closer to oxygen's nucleus is released as photons or heat.
Putting all this together, all we need is an optimal substance and heat to rearrange and break apart the bonds in the presence of oxygen.
Here I'm using a spark from flint and steel to break apart cellulose bonds.
Understanding the molecular structure of matter has more applications than you realize. This textbook knowledge could actually save your life.
Isn't it fascinating that we can rationalize the molecular makeup of almost anything to take advantage of its use? You may have not even realized it, but chemical skills have equipped you for survival. And if you're ever stuck in a survivalist situation, just remember that chemistry might be your greatest asset.